So we stopped last class in this result. So we wanted to show that if a data set, a collection of choice sets and choices from that choice sets is such that warp is satisfied, and this collection of menus actually includes all subsets of X up to 3 elements, and X is finite, right? Then we have that there is a rational preference relation that rationalizes the choice correspondence, basically with respect to a unique preference relation. Okay, what it means to rationalize, it means that I can create a preference relation that generates the data exactly. Okay, everyone agrees? So we have this equivalence. We're going to prove that. The first thing is that I want to build a model. So the part I'm going to show is that we start from warp and I create a preference relation. Okay. And remember, here the key element of this proof is the data set. It has to be all the tuples and triples, and I mentioned also that the hidden assumption in Mascolel is that the choice correspondence is not empty, right? Being not empty matters a lot because it rules out this weird stuff that we were checking with the cycles, right? So the fact that we are forcing this consumer to always make a choice is also helping the equivalence, okay? So what I'm telling you is that this is not true in general, but it is true when you have all tuples and triples, okay? So let's just start with the proof. So first, right, I'm going to define a model, which is this preference here, and this is equivalent to the data. So the revealed preference relation I got from my experiment. So again, so how did I define this revealed preference relation? This is data, right? So X is directly preferred to Y, even only if X is picked out of a choice set V, right? Whenever Y is in the menu V. So one thing is X is picked when Y is available to the agent or consumer. So the key thing is that usually the revealed preference relation is not complete, not transitive, right? But warp will imply that the preference relation when the data set is all tuples and triples, and this is called a rich data, is in fact complete and transitive, okay? So I'm going to show that. Okay, so the first thing I'm going to do is verify that the revealed preference relation under these very special circumstances is complete and transitive. This doesn't have to be the case always. So first, let's prove that this preference that I defined by means of the direct preference relation is complete. So where should completeness come? So think about it, right? So we're asking all tuples. So that's exactly what I want, right? So we want to, what is completeness is we want to check that either X is in relation with Y or Y is in relation with X for any possible pair, right? The key quantifier here is the universal quantifier for any. So that's why I need rich data. So from all the choices, it can be a million, it can be infinity, right? I need all possible tuples. Because in each tuple, because I force the consumer to always pick something out of it, then I'm gonna get that either X is chosen, right? When Y is there, or Y is chosen when X is there, right? Do you agree? So the fact that a choice is not empty, then this forces completeness. Got it? And also the fact that I have all tuples. So think of a data set where I don't observe all possible tuples, then is there any hope to see completeness? No, right? You see the issue with completeness, right? In order to ensure it, I need to observe all possible tuples. So in that sense, I told you in previous class that completeness is not really a testable condition because for general choice sets, I cannot really check all possible binary menus, right? So it will be an impossible task. So there are many choices that are infinity. So I will never be able to tell you. So think about the financial assets that an investor can have, right? So can you ask a consumer all possible pairs of those things, right? Or think about tales, you know, storybooks. Can you compare in binary comparisons, ask someone which person, you know, do they like? It's very hard, right? So yeah, completeness in that sense is only a theoretical thing, but right now we show that under this data set, it is complete. Revealed preference relation is complete. Now, the second thing is that it is transitive. So Shumei said, the definition of this thing will imply transitivity. It doesn't imply anything, right? So reveal preference alone is just a definition of data. Now, if we add the warp condition and the structure of the data, now suddenly the reveal preference relation is going to be transitive as well. Again, only on this rich data set. So right now is when we need the triples, right? You see? So we need also the triples, and now we're gonna prove that. So
sorry, a quick question. So when you say the data is rich, so is there like an infinite amount of data that's what
no.
you imply, or
so at the beginning of the chapter, I define rich data sets, the data sets that contains all tuples and triples.
Oh, okay.
Yeah, and this is, so I'm gonna add it here, so that's true. So contains all subsets of up to 3 elements, right? So these are rich data sets. Okay. Got it. So now I want to check this transitive. So what is the premise of transitivity? That take two relations, x is better than y and y is better than z. Then I want to show that this implies that x is also in relation with z. So remember, the preference relation is the direct preference relation, right? So this is the tricky part, okay? So alone, without rich data set, warp does not imply transitivity, okay? I'm telling you already that. You will have to find an example in the problem set. But right now, without the rich data set, this is not true. But with the rich data, we're gonna show you it's true. So let's start with the definition. So x better than y, what does it imply? It implies that there is some menu, right, where y is there, and such that x is peak. Got it? So that's the definition, right? Now, what does it mean y prefer to z? Same thing, another menu. I don't know which menu, right? But it has to be a menu up to size 3, b prime, and then z is there, and y is picked out of that menu. Okay, got it. So now I got the premise written in terms of definitions. Now I want to show that this implies that there is a third menu, b double prime, right? And in fact, I'm gonna let this particular menu to be the triple x, y, z. So for the proof to work, I have to have all triples, right? Because these elements, x, y, and z, are generic. So in order for this v double prime to be well defined, it has to be that my data set contains all triples. Got it? So we have the following cases, right? So right now I have to see what can happen inside these choice correspondence. I know it's not empty, right? That's the only thing I know. So the first thing is that z belongs to this, the choice correspondence for the third menu v double prime. In this case, by warp, what does it imply that z is there, right? So given that y was revealed preferred to z, warp requires that y is also in the choice correspondence of b double prime. Do you agree that warp now is doing the job here? Okay. So y has to be there. And then I also said that x was revealed preferred to y. Okay. So then warp kicks again, and then it tells me that x also must be in the last one. So x must also be in the choice correspondence. So in this case number 1, I conclude that x is indifferent to y and is indifferent to z. Okay? So that does break transitivity? No. In fact, this makes the preference transitive. So I verified case one. Now, this is a proof by exhaustion. So I'm going to check all cases. So the second case is that Z does not belong to the choice correspondence. Got it? So now, because the choice set is not empty, by assumption that it has to be either that X is in the choice correspondence, in which case X is above Z, and therefore this is transitive, or Y is in the choice correspondence, in which case by warp, X has to be there, right? Because in the first menu, X was really preferred to Y. So warp does the job again and implies that if Y is in the choice correspondence, X is also there. Therefore, it means that X is tied with Y and these are better than Z, in which case this thing is also transitive, okay? So is there any other case? Not really, right? So either because it's not empty, Z belongs there, or Z does not belong there. You see that non-emptiness plays a key role here, right? Okay. Now, okay, so what I have done now is I defined the reveal preference relation and shown that in rich data, warp implies that it is at the same time complete and transitive. So that means that the reveal preference relation here is a rational preference relation, okay? But I'm not done yet. Why I'm not done yet? Because I need to show that the preference relation I obtain from this is also generating the data, okay? Got it? So I generated a model, but I have to verify that the model generates the data. So that's the final part of the proof. So that means that we check that this C star of the rational preference I just constructed, it rationalizes the data C. So imagine I start with some X that belongs to the data for menu V, any menu V. This means that X is directly referred to Y for all Y in V, by definition, right? So the fact that you are at the top, sorry, the fact that you're chosen means that X is in direct preference relation to Y. But I already defined my preference relation with the direct preference relation, which means that if I take the items that are at the top or of this preference relation, of course, X is going to be there. So this is showing that any element in the data will belong also to the model, okay? So this doesn't use warp. So the part that I have to show still is the following. So if X belongs now to the model for a particular menu B prime, then this implies in the model that X is better than Y for all Y in the B prime menu, okay? This implies, and this is the key, that in the data, there exists some menu V sub Y. And why this is indexed by Y? Because there is a menu per item Y, okay? Such that X was picked and this particular menu. So these menus are menus that contain Y. And then when the choice correspondence is applied to this menu or the data, this show you that X was better than C of BY, the elements there. So because again, this thing is not empty, the warp implies, right, that X also belongs to the, is of course in B prime, okay? So this means now, right, that any element that is on the choice correspondence here, right, will also be in the data. This part is the hard one. It's very subtle how we have written it. But the important thing is the following, right? So I start from a model. The model was done by the generated reveal preference relation. So imagine, for instance, that I have 3 items, and then from binary menus, I reveal that X is better than Y, and Y is better than Z, right? So I already know that information. Now, when I go to the triple, right? So I say, okay, let's apply the data I obtained from these X, Y, and Z to the menu X, Y, Z. Which one is going to be at the top? So imagine it's strict preferences, so X is going to be at the top. So this is the prediction of the model. Now, I want to show that the prediction of the model is accurate, right? So the fact that X is at the top in the XYZ means that there were 2 menus, right? Other menus in the data set for which Y was present, Z was present, and then X was picked in each instance. So in particular, right, it means that for the menu V that contains the 3 items, right, X, Y, and Z. So X must be there. So again, we can check the cases. And the first case would be that because this is a strict preference relation, right, it can, you are going to have that the presence of Y in the choice correspondence in this particular CB prime will be a violation of warp. So y cannot be there, z cannot be there, and the only thing that can be there is x, right? So that's an example of what we're doing. So we have shown in two directions, right? That any element in the data set is also in the model. And then we show that any element in the model is in the data, okay? Therefore, these two sets for any choice correspondence are the same, are equivalent. Now, uniqueness. For uniqueness, note that the fact that this data set is rich includes all pairs. So therefore, we determine completely preference over pairs. So that means that there is no other possible preference relation, right? Because there is no room for wiggle, right? So this is exactly determined in the ranking, and that's it, okay? So any questions here? Okay. So this part is going to be for you for the problem set. So important caveat. So what about general data sets? So imagine a data set that is missing some tuples or triples. So missing data. It turns out that warp is not sufficient for the warranty that such data set can be rationalized by a rational preference function, right? So we need a stronger version of warp. So in particular, what I'm telling you is that warp is an implication of rationality. But if you check a data set and it satisfies warp, they may not be rational, okay? The particular previous result only tells you it is equivalent whenever the data set is rich and not empty. So we need something stronger than warp. So what is this strengthening of warp? This is called the generalized axiom of revealed preference, or the GARP, okay? So we're going to say that a data set satisfies GARP if you have two n items, x and y, such that x is, what is the symbol again? This is the indirect preference relation, right? So here we mean that there is a chain, right, of items such that x is indirectly preferred to y. So remember, this means that there exists a chain of items from I to n such that x is revealed preferred directly to x1, and this is revealed preferred to xn, and basically this is revealed preferred to y, okay? Everything directly. And if that happens, then it is not the case that y is strictly directly revealed preferred to x, okay? So who gets what's the difference here? So the first one is just direct inference, right? So if you choose something out of a menu, when another alternative is present, then you say this first item that was picked is directly preferred to the other, right? And then that's the only thing you use. Here, you're using indirect inference because you're saying, look, if you have a chain of these revelations, then I can also extrapolate it, okay? And this is a transitive closure, if you recognize this for chapter 1. So what is the result here? So the result here is that take any data set. It may be incomplete in the sense that not rich. And let this data set satisfy its GARP, okay? This is equivalent to the choice data set structure, the same one, can be rationalized by a preference relation, okay? Got it? Okay. So let's do this in reverse. So I'm gonna show first necessity. So I'm going to, what is necessity? I'm going to show the direction 1 to 2, okay? Sorry, necessity here is gonna be 2 to 1. So you have something that is rationalized by a preference relation, and then the data set is going to satisfy GARP. So GARP is a testable implication of rationality. That's the first thing I'm gonna prove. Assume towards contradiction that GARP fails, okay? and that the data set is rationalized by a preference relation that is rational. Okay, in other words, imagine that you have a violation of GARP. So X is indirectly revealed preferred to Y, and at the same time, Y is directly and strictly revealed preferred to X. Okay, so here you have a cycle, right? These preferences are being flipped, but indirectly. So this is the stronger version of work. So now, this happens for some X and Y. Now, because this is a result of maximizing our rational preference by assumption, right? I'm trying to reach a contradiction. It follows that X, of course, in the rational preference is preferred to Y, and Y is strictly preferred to X. So in particular, I know there is a chain, right, of these preferences, X better than X1, better than X2, and so on, until I reach, of course, this strict preference to X. So this is a violation of transitivity, right? Do you agree? Because this will imply, of course, that X is strictly revealed preferred to itself, which cannot happen, right? And so it's breaking reflexivity, which is an implication of completeness and transitivity. So this is one of the things that you can prove from Mascolel, or you can read it there. Complete and transitive relations are also reflexive, right, in the diagonal. So X has to be pretty much in difference relation with X. So this is breaking transitivity. So we have a contradiction. So we have proven that 2 implies 1. Okay, this one is easy. So if you're rational, then it implies that you satisfy GARP. Got it? And now let's prove the hard one, right? And for the hard one, we're actually going to use high-level math. So I told you to check the first chapter, right? And in particular, I told you to check this extension theorem. So who remembers the theorem, right? And what does the theorem say? The extension theorem in proposition 1, I think. So who wants to give it a try? Else, we name someone? Maybe Zach. Can you hear me, Zach?
I honestly don't recall that.
Well, the pronunciation is hard, right? But it's basically this theorem that I sent you in the Slack. So the pronunciation is Silrajan. I don't know how to do it, but this particular theorem, theorem 1 in the first chapter, right, is telling you the following. It tells you that, so can you remind us, Zach? So just read it from the Slack or from the notes. So theorem 1 is Silrajan.
Sorry, did you say it's on the Slack?
Well, we have our communication device, right? Decision theory fundamentals.
Yeah.
Yeah, so I wrote there the theorem 1, but also you can go to the notes to the first chapter, and then you can check there this extension theorem. So it's theorem 1 in the first chapter. So you can also check it here. So, okay, let me show it to you. Okay. So again, so try to check these things as I told you before the class. So in chapter 1, order theory, right?
Yeah.
Here we have this theorem, okay?
Okay.
So what does it say? So it says, can you read it?
For any non-empty set X and a partial order on X, there exists a linear order that is an extension of the original relation on X.
Okay, great, thanks. And we also, and one thing that is, so the proof is omitted, okay? So it turns out that the proof of this is really hard. Well, it's hard for us, right? But it's a classical proving math. And also in the corollary one, that the proof is written in these notes that you can read it for your benefit. It says that we can also take a pre-order set instead of a partial order, right? And also extend it, okay? So what I'm saying, do you get what I'm saying? This is not as simple as it seems, right? So for instance, I'm gonna tell you what I'm doing. So imagine I have, right now I'm going to go to the world of OLS, right? So you have a scatter plot of points. And imagine there are some lines, right? And I can do interpolation. So there is no noise. So there is just the lines that are scattered, right? And my objective is to pass a line through all the points, right? Interpolation. That's what I'm doing. So under what circumstances can I take a cloud of points, right? And draw a continuous line across them. So I can always do that, right? So without properties, I can always do that. So that's kind of easy. What is not easy is that, imagine for instance that now I want to take a cloud of points, and I'm going to go now to the InVision, to the board. And what we're going to do here is that I'm going to tell you what happens, for instance, if you have a cloud of points that may not have a property such as being decreasing slope, right? And in particular, I'm going to share now the InVision. So can you see it now? Yeah.
Yes. Yes.
So imagine you have this cloud of points. Okay. So can I take this cloud of points and create a continuous line that is always downward sloping? No, right? Do you get it? So there is no way I can interpolate it, right? But imagine now that, for instance, I deleted this particular thing. So can I do it now? Absolutely, right? I can just take this, this particular one and draw this line. How many lines can I draw here that are downward sloping? So this one is in particular not a downward sloping, so I can make a straight line, something is more curved, right? Many things. In particular, the important thing here is that what I'm telling you now in this resolved order theory is about extensions of a particular, pretty much a function, right? So in preference relation is a form of mapping. And what I'm telling you right now is that whenever you have something that is a pre-order, right? That is transitive, you can take it and then extend it to the whole space, okay? So the significance of this theorem is telling you that start with a pre-order, right? That may be partial, not complete. That's the key. And you can extend it to the whole choice set, making it complete, so drawing the line, right? With the properties intact, okay? So in particular, this will preserve the weak preference relation and the strict preference relation, okay? This is an extension. So please, remind yourselves of this in this chapter, right? But the key thing about extension is this. So if you have some relation that in particular pre-order, it has to be that the extension is a complete relation of the choice set that preserves the weak and the strict part, okay? Got it? So what I'm doing is interpolation. So start from an incomplete relation and extended it to the whole choice set. Got it? So this is ensuring that I don't have this weird stuff that I show you in the graph about impossibilities of doing interpolation with a certain property, okay? So I'm going to go now to back to our chapter. Back to our chapter, and then, sorry, this is chapter 4. And here we're going to show this part, right? So remember, I want to create a preference relation that is complete and transitive, okay? Completeness is the hard thing because right now we may have an incomplete data set. So we may have something that is not rich. So, okay. So first of all, take what I call I'm going to define the strict indirect preference relation, right? And this is going to be the asymmetric part of the indirect preference relation, okay? In other words, it will be A is strictly will prefer to B, even only if A is in relation, indirect revelation that is preferred to B, but not the other way around, okay? Now, GARP will imply that the strict direct revelation is in this asymmetric part. So do you agree with this statement? So in particular, think about GARP. So imagine this is false, right? So imagine that this direct preference relation is not there, right? So then, you know, it will violate GARP because it means that, as the definition says, right, this particular part can happen, right? So the fact that I'm ruling out this, right, it is not the case that this happens, means that this start relation, which is the asymmetric part of the indirect revelation, contains the direct strict revelation, okay? Now, the other thing I can do, right, is showing that the indirect preference revelation is the transitive closure of this direct preference relation. So this is just by definition. I take the direct preference relation and I define the indirect preference relation as the transitive closure, okay? So I know there is this chain of revelations, right? So this will make it by GARP, this will make it a transitive closure, and a cyclicity or GARP implies that this thing is in the transitive closure, okay? So now with these two things together that are implied by GARP, now it means that this indirect preference relation is what? Is basically a pre-order that is incomplete, right? Can you tell me why is a pre-order? So what are the properties of a pre-order? So from chapter 1, right?
Complete and reflexive.
Yeah, so in particular, we're gonna check that it's transitive, right? That's the main thing, the important thing. So so take by GARP pretty much, no? Take any relations that are in the relation, right? And you have X is indirectly referred to Y, and Y is indirectly referred to X. Then it must imply that X is in indirect relation with Z, and Y, because if not, then you're gonna have a violation of GARP, okay? So GARP here is gonna imply transitivity, and we have pretty much this. This is a partial order. Now, with this in hand, remember the only thing we're missing is that completeness component, right? So we need to extrapolate to do the interpolation to be able to extend it to the whole choice set. So now we can use the extension theorem, right, in order theory to claim that there exists a complete and transitive preference relation such that X preferred to Y implies in the constructed extension, which is without a star, also implies that X is preferred to Y. And of course, the strict relation also implies that a strict version of the rationality holds X is strictly preferred to Y. Now, let's start from the data now. Say that X is in the data from menu A. This implies that X is directly referred to Y for all Y in A. Now, by my construction, the extension theorem, X has to be better than Y for all Y in A, okay? And now imagine now that X is not in CA, and this implies that there exists a Y such that Y is strictly preferred to X. And this implies, of course, by the extension that Y has to be strictly preferred to X and not X better than Y. So together, this implies that the CA is in fact the set of maximizers, okay? Now, this construction is really relying on the existence of this extension theorem, okay? So at this stage is super general and hard to understand. I'm going to do a version that is way more constructive. So constructive, I mean, is I'm actually going to build this total rational preference relation as I did with the warp, right? Remember with the warp, I did it constructively, okay? Here, I instead did a proof that is an existential proof. So I claim that there exists an extension. So do you see the difference in the nature of these proofs, okay? The proof of the previous term is easier to understand because it's a constructive proof. I created a model using just the data and defining things from observations, right? In the second one, I invoked this theorem from chapter 1 to create an extension, basically to say that there exists one extension that does what I want without actually constructing it, okay? This is something in math that is called the axiom of choice. So it allows you to claim that some mathematical objects exist and you can use them without actually telling the reader or which is the object, in fact, right? So this is a non-constructive proof, okay? So here we're invoking from math the extension theorem. So let me tell you this in a little bit of simple words. What we're doing is fundamentally the following. So I'm going to give you an example. I'm gonna create an example here. So imagine I have a simple data set. I have here A, B, C. This is my choice set. My menus are A, B, B, C, okay? Now, and my choices are out of AV, this agent chooses A. And out of BD, this agent chooses B, okay? And in order for GARP to actually have meaning, I'm going to introduce also the menu AD. And here I'm going to describe the choices of this menu as well. Okay. So first thing I want you to do is to verify GARP here, okay? So I want to ask one of you. So maybe Yongking, so tell me why this satisfies GARP?
Sorry, I don't really know why it satisfies GARP.
No, go to the definition, right? Definition 29, okay? What is GARP? So GARP says that if you have a chain of objects, right?
Mm-hmm.
So each of them is direct revelation. So X is big when the other object is present. If you have this chain of things, then the fact that X is revealed preferred to Y, it implies that Y cannot be revealed preferred to X, right? So
can we go back to the question?
Now the question is, in this particular data set, this is my choices.
Mm-hmm.
Prove that this data set satisfies GARP.
So I think here we also have a chain. So it's A is better than B and B is better than D. So when we so it's not the case that D is better than A.
Okay, so let's write it down, right? That's perfect. So this is strictly and directly referred to
Mm-hmm.
B, right?
Yes.
And then this thing is strictly and directly referred to D, right?
Mm-hmm.
And you know, by GARP, I will never have that D is strictly referred to A, right?
Yes,
So
I think you meant to say B is indirectly revealed to D. Yeah.
Yes, and not, right?
Yes.
Okay.
Mm-hmm.
So this means basically that this is satisfied here, right? So GARP holds. Okay. So by GARP, what is the relation I constructed? So the candidate relation. So A, in fact, is better than B, and this is better than B. Okay. Yeah. So in this particular case, there is no need for extension theorem, right? Because just from the data, I already got my preference, right? GARP already implies rationality. And for this particular case, because I have so little points, I don't need to extend it. Now, what about this? Imagine now I have, for instance, a third item. So here I should modify it. A third item E, for item E. So, so now, again, I check my data set. I don't have all subsets, right? So now I don't have all tuples. GARP still holds, got it? But now there is something new. I have this relation, right? Which is the indirect preference relation, which is strict. But this is not still a complete transitive order, right? Because where is E? E is not rank, right? So my theorem is telling me that I can always complete this relation, extended, respecting the strict part, to the choice set, still keeping transitivity, okay? So I know this can be done, right? So the theorem tells me this can be done. Now, because this is so easy, in this particular case, I can construct such extension, right? One of many. So in particular, which one can work? So this implies, my theorem implies, let's say, previous term, implies the existence of a preference relation that is complete and transitive on X, right? So in fact, we verify this by constructing, for instance, I will put E at the very top, right? E is better than A is better than B, and B is better than D. Is this the only rational preference relation that I can have with E? No, right? You can construct many others, right? And the only requirement, the only constraint is that you have to respect the strict preference relation. So tell me another option, for instance, Faye.
You can construct A is preferred to B, B is preferred to D, and D is preferred to E.
Yeah, so E can also be the worst item, okay?
Yeah.
You see what is the issue, right? So the only requirement is that still A, B, and D will be strictly preferred to each other, right? And by transitivity, for instance, this will mean that if E is at the bottom, also it will be that A is better than E strictly, right? So all these things will be restrictions for our interpolation, but we can complete in many ways. So what we lost in this theorem from the previous theorem? We lost the uniqueness, right? So here I never claim that the recovered preference relation is unique. In fact, it can be multiple. I can recover multiple models that will explain the data as well. Got it? So everyone's on the same page, okay? Now, so something I will ask you to do in the problem set is to come up with a data set that satisfies warp but fails guard, okay? So start thinking on that. So I'm gonna tell you again. So there are data sets, and I'm asking you to find one that satisfy warp, the weak axiom, but fail guard, okay? So with this part, we're gonna complete the study of this section telling you that warp is not sufficient for rationality, right? In general. It is only sufficient for rationality when the data is rich and you're assuming non-emptiness, right? Okay, got it? So this is the previous result. And the one that is necessary and sufficient always is the guard, okay? So guard, the one that we show, is always good, okay? So, so another thing I told you is that you can have data sets that pass the weak axiom work, but fail guard, okay? That also is true. So this one you have to do in order to understand this. So questions here? Else we're gonna go to the next chapter.
Yeah, sorry, go
You
ahead.
can go ahead, David.
Would GARP imply warp?
Yes,
Okay.
good point. So if you have a data set that satisfies GARP, right, warp holds. What is the proof? Super simple, right? A warp is GARP when the cycles are of size 2, right? So is the chain is the smallest possible chain, okay?
That was my question.
Okay. Now, great. So that's exactly. So the length of the chain is the one that changes between GARP and warp. Good. So one thing I want you to realize, and this is very powerful, right? So what I just gave you is a generic test for rationality, right? So I'm gonna ask you to do this in the problem set. So I'm gonna ask you to send a survey for, I'm gonna send a survey to you, to all of you. You're gonna fill this survey from choices, right? And we're gonna collect your choices. So this is going to be a real life data set. And then I'm going to give you this data and you can check GARP there. And you can see which among you is rational. So you're economists, so possibly you're going to cheat and all of you are going to be rational, but it's more about checking, right? But the point is that this is very powerful because this tells us two things. Utility maximization is going to be testable because we can always test whether GARP is true. There is a wrinkle, however. So what happens, for instance, if we allow everything to be indifferent to each other, right? So in particular, imagine that we have here the strict part is the one that creates these restrictions of the data, right? But in particular, imagine a preference relation that you are indifferent among everything, right? So this is one of the issues of rationality, right? Because this is a too irrestrictive model. So if you are indifferent among everything and you run a finite experiment, then, you know, if you observe an agent picking different things from the same menu, it can just be telling you that they are indifferent among them, right? So in particular, you need to add an additional restrictions to rationality in order for this to be a non-trivial model. So do you get what I'm saying? So imagine you now become an experimenter. You want to seriously test this model, right? And now you start collecting data. And so you present the subjects with the menu X, Y, okay? And the first time they choose X, right? Then the second time they choose Y, right? So if you, for instance, are testing the version of rationality with a strictness, then you will for sure reject this model, right? First, it picks strictly X over Y, and then Y over X, right? But imagine you didn't have the strict part. You are allowing everything to be indifferent. So the first time they pick X, and the second time they pick Y. So depending on how you're recording the choice correspondences, you might actually say that both X and Y are choosable, right? So therefore, you see the difference between experiment and choice correspondence. Choice correspondence is this theoretical object that the agent already told you everything that is choosable for them, right? But in the experiments, usually you have to have some protocol, and the usual protocol of experiments are that each trial subjects are asked to pick one item, right? Okay. So if that happens, then, you know, every time you run the experiment, then you may actually still be writing down the choice correspondence. So in particular, right? So the version that usually people check in laboratories is the strict preference, right? Indifferences are usually ruled out because of this. Now, indifferences, let me put it like this. They seem reasonable, right? In real life, because you may be well indifferent among two things, right? But the issue with indifferences is that, you know, are they really the fact that you have the exact same preference for them? Or is it, for instance, the fact that you cannot tell them apart, or maybe you don't care among them, or maybe you don't know how to pick among them, right? So so the issue with indifference is that, in fact, it's a very hard object to study in real life. So what I'm telling you is that in most applications, in most things, people use usually the strict preference, right? And indifference is kind of ruled out. Or then other solution is to augment rationality with additional constraints. In particular, we're gonna add to rationality monotonicity. So in the world of consumer theory that we're gonna go in a second, for instance, rationality will respect the orders of vectors. So you're rational, but also you will like more to less. So if you're given a vector of commodity value, which is a vector that has more of every good, then you will be forced in our theory to pick it over a commodity value that has less of everything, right? So that's going to be the refinement of rationality that we're going to see forward, because this is what is testable. So, but in general, this is a really cool result because you can take many data sets in many environments and then just apply GARP and just check whether your data set satisfies rationality or not, right? So that means that rationality is testable. And not only is testable, it's also testable in finite data and also non-parametrically. So you don't need to write down a utility that is Cobb-Douglas, for instance, to test it and estimate it using econometrics. You can just take the experiment and test it directly, which is really cool, right? Now, of course, then the next question would be, is rationality a good model? And we're going to discuss that later, okay? But there is a big discussion about it, whether this is a good model or not. But the first step to know whether you have a good model is to have a way to test it and to measure it. okay? So now, chapter 3. So first of all, as I mentioned in the message board, in Slack, I told you that I eliminated pretty much the previous chapter 5 because this was redundant with the things that we saw in the summer. Usually I kind of do an over review of that because following Mascolel, he does this warp theory that I already did in the summer. So I'm not gonna do it again. In this time, I'm gonna focus on different topics than in previous years. So in particular, the previous chapter 5 was eliminated. And I just went directly from chapter 2 in Mascolel that we already saw in the summer, and in the chapter 2 in our notes, to chapter 3 in Mascolel, which corresponds to chapter 5 now. So the topic in particular is consumer theory or utility maximization, okay? So be warned that the new notes have the updated material, right? And I also updated some results and proofs here. So what is the purpose of this chapter? So it's gonna look hopefully familiar to the things that we saw in the summer, but it's gonna have a quick, a key difference. The difference is that instead of studying demand functions here, we're gonna study demand correspondences, okay? But the object of interest are gonna be the demand function. So we're gonna get back to this world of prices and income, okay? So we're gonna get back to that. Previous chapter was the most abstract decision theory. So our consumption sets can be anything, right? It can be discrete things, so X versus Y versus Z, a set of lotteries, a set of cars. Here we're back to commodity bundles, okay? So the choice set is again X, which is a commodity bundle. So just, I'm gonna remind you this thing. So the choice set here, I'm already writing it later, so I'm gonna show you. But let's write like this. Right, so here this choice set is RLX, and in fact we're gonna let things to be non-negative, but they can be easily non-negative. So the theory doesn't depend on that, and in particular, L is the number of goods, and is fixed. It's the same thing as the summer, and in particular, I'm gonna let P be the set of prices. So here they're gonna exclude 0, so they're gonna be strictly positive. And W, the set of W is gonna be the set of income levels, which is going to be also strictly positive levels of income, okay? So this is where I'm choosing now, is an infinite choice set. And I'm going to define here demand correspondence. So demand correspondence is gonna map pairs of prices and income to a subset of the choice set. So in particular, you're gonna see objects like this. So if you have an X that belongs to this choice correspondence, right? This will in fact mean that X belongs to the X set, right? So you're mapping price and income to a set, and any element in that set belongs to the choice set, okay? And in particular, the key restriction here is that they're going to satisfy the income. They're going to satisfy the fact of budget constraint. So they must be such that the multiplication of prices times the element X is going to be less than equal than income for all X in the XPW, okay? Remember, XPW now is a set. That's why this notation works like this. So the first thing that I'm going to tell you is how we're going to map this with the previous chapter, chapter 4. So in the previous chapter, we were dealing with choice correspondences, very generic ones. So they were giving me a choice set, and I was giving you the choice out of that. So here, instead, this choice correspondence is going to be defined in terms of prices and income. But remember that prices and income are really giving you budget constraints, right? So a budget set, which is a set, right, is all the sets, all the items in X, capital X, that for a given price and income, right, they satisfy this inequality. P times X less than equal than that. So this object here, right, is in fact a choice set. So this is a particular case of chapter 4. Do you agree? So in fact, we're seeing a special case of chapter 4, okay? We are going to add more structure, so we're going to get more results, but it's a particular case. So how do I define the demand correspondence? Well, the demand correspondence is nothing else than the composition of a choice correspondence that we studied in chapter 4, composed with a budget correspondence, right? So it's the composition of two correspondences, and this will now map, as you can see. Prices and income are mapped through the budget constraint, right? Are mapped through the budget correspondence to the collection of budgets. And then from the collection of budgets, the choice correspondence C is going to map it to a subset of the power set of the choice. Okay? So this is what's happening. And let's illustrate this by an example. So imagine I have two goods. And now my choice correspondence is going to tell you entry by entry what I'm going to choose. So in particular, it's going to be a point, a choice function, whenever price of one is less than price of two. And it's going to be the same whenever price of two is less than price of one, also a point. But whenever price of one is equal to price of two, then you have a set. So anything can happen between the interval 0 and W divided by PI. Okay? So this is a demand correspondence. Okay? So what is new here is that instead of having from prices and income, I get exactly what you consume. Here I'm getting a set of choosable items. So same caveats apply. Why do we do this to us as theories? Well, choice correspondences are very hardly used in empirical data, right? But they are nice for theoretical purposes because they allow us to deal with this possibility of indifference, and they also simplify a lot of proofs. And you also want to see it in the most generality possible, right? Because there is a kind of a feature that all theories were trying to implement these models. They were trying to allow the possibility of having choice correspondences as a way to make less precise predictions, right? So
quick question. For this example, I guess X1 and X2 could be said as perfect substitute, just to understand the notation correctly.
Yeah, so remember, this is a well-rationed demand correspondence that may or may not come from utility maximization at this stage. You recognize that this can be rationalized by a perfect substitutes utility, right? Now, that doesn't mean that comes from it, right? This is just data at this stage, okay? But good question, right? So of course, it can be rationalized. Now we're gonna learn under what circumstances I can say for sure this can be rationalized, right? And this is gonna be a GARP condition, okay? Good. Again, so why do you think we need demand correspondences? Do you think it's good or bad? So think of yourselves now as modelers. So tomorrow you are hired by Amazon, right? Amazon is hiring a lot of economists, so it's not unlikely. And now, right, they ask you to model some demand data. Okay, so what is demand data? You see prices, income, and then you see choices. Okay, and then you know under what circumstances is good to think about functions versus correspondences, right? So what do you think are the pros and cons? So maybe Eduardo can tell us your perspective. It's purely opinion, right? It's not a quiz question.
Well, for example, like you're saying in Amazon, maybe using like a correspondence might be advantageous just because of the variety of choices that you have based on price and income. If you had a much simpler choice, then probably like a function might be better in that case. But I guess what you're in the business of looking into is kind of what different mixtures of choices, or like what possible choices do you have based on these parameters, right?
Well, so I guess you're right? So it depends a lot on the data, right? So previous the data set we have were very poor. So you usually could see people choosing just one time, right? And then you see possibly they chose just one bundle, right? But imagine in Amazon, we have, people are buying daily stuff. And then, for instance, maybe imagine they are buying their groceries online, like Instacart or Amazon. And, the first day they pick a combination of bread and butter. The other day they pick wheat, so another kind of bread and also butter. Do they actually prefer one to the other? Are they irrational because they change their preference, or are just indifferent? So I don't have a strong answer for you now. I think the important thing that we have to recognize is that there is always a gap between what theorists think is important and what applied people think is important. What I think is important. What I'm going to tell you for sure is that applied people I haven't seen a paper using demand correspondences, right? At least in terms of econometrics. However, they turn out to be kind of handy in a new branch that is not demand estimation, but is rather set identification, right? And I'm going to tell you more about that as we end this chapter. And we're going to see that demand correspondence may have a role just because we want to allow for being non-parametric in the utility function, right? So we don't want to make strong assumptions, right? So part of making very weak assumptions may be allowing indifference. So it's going to be part of a bigger picture. But in particular, right now, you want to know that demand correspondences are kind of a generalization of demand function that may not be completely relevant for you in the long term, right? But we're going to learn them because they're going to become important as tools for theory. So if you mature for game theory, you're going to use a lot of demand correspondences, right? And they may become relevant in empirical work later on as people get more sophisticated. But right now, you're going to never see them again except in theory, right? So I want you to kind of compartmentalize, know how they may come handy. But the main important thing I want to tell you is, and I want to emphasize this, is that, this kind of a statement saying, if prices are equal, anything goes, as long as it's affordable, are not informative, right? So for instance, if you're hired by Amazon and they tell you, okay, so imagine that I fix the price equal to each other. So what is going to happen? And the theory is going to tell me anything goes, right? That's kind of a poor thing to say. So what I'm telling you is that this is kind of, as I told you in the previous class, this is kind of 60 data set, 60 predictions. So it's kind of lame. Right now, there are better stuff. And this in particular, the substitute for this is a stochastic choice. So I may not be able to tell you exactly, what they pick, but maybe I can tell you distribution over these choices, right? So we're going to study that later. In fact, I'm going to do this for next week. So you're going to see new content. But right now, we're going to focus on this old stuff that is called basically non-deterministic, but also is not stochastic, you see? So anything goes, but we don't really know with what probability. Do you see the difference? So this statement here tells me anything goes, but I am telling you any probability over that? No, right? So there is no guidance. So it's not uniform. It can be anything, right? So because there is no distribution, then it's very uninformed, okay? So we're gonna keep going, but have that in mind. And again, mathematically is gonna be good for maturing as knowing tools from math. When you learn game theory, you're gonna use a lot of correspondences, okay? So that's gonna help you a little bit also for that. And continuity, right? So we're gonna define the notions of continuity. And remember that for functions, this sequential continuity was very easy. So you take in the domain a sequence of prices and income, and they converge in some topology here to PW. And then continuity in the sequential version for this very simple Euclidean space was telling me that the sequence of images in the function x, p, n, w, n also converge to the image of the limit item in the domain. So now, what is continuity for correspondences? So again, in the Slack, I send you a reminder. You can also check it in the Mascolel math appendix. What is semi-continuity? So you can check there. Also, Maria is going to teach you that. What is upper semi-continuity, lower semi-continuity? These are extensions of continuity for these correspondences, okay? And in particular, upper semi-continuity has the following definition, right? So X is a choice correspondence, and then you have a sequence in the domain. And then take now a sequence in the set. So you have a sequence of sets, and now take a point in those sets, and now create a sequence out of them. So this is a selection. And there has to be now, this sequence must converge to a point in the choice set that happens to be a part of the set that is in the limit, right? So as I sent you in the appendix, and I'm not gonna draw it for this particular class because I want to spend time in something more important. So you can check the wiki. Is that this is a weakening of continuity, right? that also is well defined for set value mappings instead of just point value mappings as opposed to functions. And in fact, upper ME continuity is the only thing I'm gonna be able to get generically for the demand correspondence coming from a utility maximization. So in particular, example 15, this is something you can also check if you want. I'm not gonna do problem sets about that because that's for Maria, and that's what she's doing. You can check that this example 15 is in fact upper ME continuous, okay? So it's an upper ME continuous correspondence. And of course, it's not gonna be continuous, right? Because you have this set value object. And now, another properties that we're gonna need to know is that choice correspondence is called compact value. If for a fixed P and W, this set is compact. Because our set is nice, is Euclidean, this is gonna give you sequential compactness, and it means that you have xn and it's gonna compare, so it means it's close. And you're gonna have also that it's bounded. So close and bounded in this particular Euclidean space means it's compact, right? So here is way more simplified, okay? So it's a closed image and it's bounded as well. And it's gonna be bounded because we're gonna have bounded income and so on. So the correspondence X is convex value. If the set of any P and W that is chosen is you take any two items there and they also belong inside. So convexity is gonna be important because when you have indifference, you're not gonna get unique maximizers. But the nice thing is gonna be that under convexity assumptions, you're gonna get convex maximizers. So this is gonna tell you that the image of the demand correspondence is gonna be at least convex, okay? And convexity in principle is useful because, for instance, say you actually implement this in real life and you get set identification. So then instead of checking all possible points in a very weird set, very weird shape, with convexity, you can actually check just the boundary, right? And then everything inside will be contained. So you only have to find the boundary. So, but here is gonna be a property that is gonna be useful for us in our proofs. And is just a consequence of utility maximization. So I'm just telling you the definitions. Now, these are technicalities. I want you to learn them, but they are not conceptually important. Now we're gonna get to something more interesting. And this is something I've been promising since the summer, which is the full proof for the utility representation theorem, okay? So in particular, so right now we already proved with GARP that if you can always take a incomplete order, right, and extend it, okay, great. And this order is gonna be complete and transitive, right? And we know that GARP is equivalent to this complete and transitive order. Now, this is cool and everything, and you can test it and you can do experiments. But if you want to model stuff, using binary relations is really hard. So have you ever tried to maximize a binary relation? So it's really hard. Unless your problem is finite, it's super hard, right? So you need something easier. And what people have learned because of physicists, the math that has been developed a lot, and we know a lot, is calculus, right? So when was calculus invented? I think in the 18th century, right? So it's very old. We know a lot about it. We have software that does this. You can use Julia, R, MATLAB, Mathematica to optimize these GAMs, right? So a lot of software does optimization using calculus, right? How many softwares do you know that does optimization using binary relations? Yeah, maybe Mathematica, right? but the others know, right? And so you want to go into a world where math is easier. And you know, another reason is that economists became so good at using utility functions that now actually utility functions is kind of a second language to economists. So basically becoming an economic modeler is writing a story by means of a utility function, right? So that's economic modeling. So you write down a utility function that tells a story and explains the behavior. So can you do that with preference relation? It's harder, right? Maybe you can in another world, in another, that people develop that math better, a better language for that orders, then people can do it, right? But, you know, just the utility functions are easier. They come at a cost, and the cost is that you have to assume something else. This is a technicality because continuity is not testable. So we're gonna assume continuity. Continuity means that take a sequence of bundles, xn better than y, and then take this sequence of xn and then let it converge to x. then continuity implies that X also will be above Y, okay? So you are not flipping. And I told you this example with lexicographic preferences. Again, we are ruling out lexicographic preferences. Mascolel has a full section trying to show you why lexicographic preferences cannot be represented by utility function. Is nice, do it, you know. And for me, that's not that very important, you know. In particular, why is not very important for me? Because I'm data driven. So continuity is completely untestable. So in real life, you can never tell apart a preference function that is continuous versus one that is not. You can never see preferences. So if you see the man generated by lexicographic preferences, they are going to look like coming also from an additive, almost perfect substitute kind of one. So there is always a continuous function that generates the same data that a non-continuous one. Do you see? That's what I'm saying when it's not testable. So lexicographic preferences, for instance, are theoretical interesting, but they never happen in reality because I can always find a continuous, well-behaved one that does the same thing as the lexicographic one, right? So when I say something is a technical assumption, it means that I can do it without any loss, you see? So continuity is without empirical loss, okay? So I can always do it. Now, footnote, if you see a model claiming to do something new about behavior and it depends a lot on discontinuities, it's a lame model, right? Because it's completely untestable, right? And I have seen some models, especially in behavioral econ. Discontinuities are weird and undesirable and are not testable, right? So we're gonna assume in general continuity, okay? And we can do it because it's not testable. Okay, so now we have the preference relation that is continuous rational preference on this Euclidean space. And for now, and then, you know, as remember that this thing is going to be, we're gonna create a continuous utility function that represents the preferences. So what does it mean for a utility function to represent the preferences? So who remembers this from the summer? So let me quickly do it. Okay. So I'm just gonna write it. Okay, so it means that I have any two x and y in X, right? And it has to be that if X is in relation with Y, this happens if and only if U of X is greater than or equal than U of Y. This is a representation, right? Theorem. So this means that it represents. Okay, so the proof is gonna have two parts, and it's gonna be, the first part is gonna be easy, constructive, and the second part is gonna be non-constructive, okay? And the idea of the proof is the following. Remember in the summer, we proved a version with a finite set. What was the intuition of the proof? So I pretty much started with the preference relation, and I detected a lower contour set, right? All the items that are worse than an item, right? And I pretty much defined the utility as the cardinality of that set. Do you remember? So the idea was that items that were higher up in the ladder, so prefer to the items, do the other items, so the most preferred items, they have a larger lower contour set, right? So therefore, the utility can define as the cardinality of the lower contour set the items that are worse than the item of interest. It was a utility function. So it's a numerical representation of the binary relation. Of course, it may not be unique, but it's even only if, right? Logically equivalent, an ordinal equivalence. Now, what is the complication here? The complication here is that I have here an infinite data set. So with infinite data set, I cannot just count things, right? So imagine that I have here, for instance, an item X, and I'm looking at the items that are below it. So can I tell you the cardinality of that? Well, if it's infinite, not really, right? It's infinity, right? So it's not good. So what I'm gonna do is the following. I'm gonna take a choice set that is the set of all rational numbers. So we're using rational in two senses now, right? So Q is the set of all rational numbers. What is a rational number? So who remembers the definition here? So it's just all the items that, all the numbers that can be represented as a division or ratio of two integers, right? So for instance, 1/2, 1/3, and so on, right? So those are rational numbers. what is an example of a non-rational number is pi, right? So this has infinite digits. I cannot represent as a fraction, okay? So now, what is the property of the rationals in the space of the reals, and therefore in the product space QL and the Euclidean space RL? The key property is that the rationals are what is called dense inside the reals, okay? So who remembers the real analysis? This is the time you're gonna use it. So what does it mean for a set to be dense in another? Who wants to give it a shot? Maybe Brice? No. So being dense inside another set, right? It means that if I take a sequence of elements, so think of the rational numbers on the real line, right? So you have numbers such as 1/2, 1/3, and so on, right? And you have pi. Pi is not there, right? So now, what I'm telling you, what it means to be dense is I can create a sequence of fractions, right? That eventually will converge to pi, okay? So in particular, take any number in the real line, right? And I can always create a sequence of rational fractions that will converge to that number. So in particular, an example is take pi, right? And you can always take a sequence of fractions that will converge to that point. Got it? So that means to be dense. So do you see what's happening now visually? You're visualizing it. So we're gonna use a rational, we're gonna use the set of rational numbers that is dense in the reals. And the second feature about this is that the set of rational is also countable. So what it means to have a set that is countable. So being countable means that you can put it in a one-to-one relation with the integers, right? So I can actually assign to a fraction an integer number, right? Got it? Even if it's infinite, right? But I still can count them, okay? So with those two things, I'm going to use a similar technique to the finite case. So take the lower contour set of an item X, and this is all the items Y in the rational subset, right? QL, such that X, of course, is better than all items there, Y. So this is the lower contour set. Got it? So this set is countable, even if infinite, right? But it's countable. So now it's countable infinity, right? So now we can define an index set. So these are set of integers such that there is an isomorphism between the integers and the elements of the lower contour set, okay? Do you see what I'm saying? So I'm assigning to each of these bundles, which are vectors, right? I'm assigning a number to them, okay? So I start counting them. So the order doesn't matter between them. It just matters they are below X. So this is the collection of all items there. I can put an arbitrary indexing, okay? Now, I'm going to define a utility function. So this is a candidate utility function. U of X is going to be 0 just to create an anchor, but doesn't matter. And look at what is happening here. This is the summation of all fractions 1/2 to the power of I being an item in this integer set, okay? So this is a sequence, right, that I'm summing. And the important thing here is that this is always going to have an upper bound of 1, right? And a lower bound of 0, you see? So it's never going, is a convergent sum. So this is from calculus. 1 to the divided by 2 to the power of I going from 1, 2, 3, and 4, and so on. It actually will always, the sum will always be less than 1, okay? Do you get it? Okay, the important thing is that this is a number that is not going to blow up to infinity. It's going to be bounded between 0 and 1. It's always well defined. And more importantly, the number itself depends on the size of the lower contour set. Here is where countable infinity matters. Do you understand? Okay, so what I want to do with this is I want to show that if X is in relation with Y, so X is preferred to Y, then the utility of X that I just constructed has to be greater than or equal than the utility of Y. And how do I do it? Well, it's simple. I'm going to use transitivity. So say that X is better than Y. I already proved in the summer that this implies that the lower contour set of X has to be a superset than the lower contour set of Y. Do you agree with this statement? right? The item that is preferred, X, has to have more items in the lower contour set than Y, right? By transitivity. So you can check it. So any item here belongs to this set, okay? By transitivity.
Sorry, can we, sorry, I'm kind of going back a little bit, but so NX, so NX represents the number within the set? Sorry, I wasn't sure about the NX there.
Yeah, so, okay, so let me do an example. Yeah, so let me do an example. So imagine that you have the lower contour set of X being the following object, right? So imagine it's just the reals. So X is just the reals, so one good. And then you have the lower contour set of X. This is actually even, it's some subset of Q. So just some set of the rationals, right? And is a strict subset. So then X, let it be any fraction, and then the lower contour set be this item with 1, 2, 1 half, 1/3, okay? So then, you know, N of X for this particular preference is going to be just 1, 2, right? And I assign 1 to 1/2 and 2 to 1/3, okay? Imagine that I have now something else here, like 1/4, right? Then I have to add another item here. So in particular, this thing here is going to be just counting the items there. And they have to be of the same size, right? So the bijection means that I can always map one index to a fraction and the other way around. Now, in particular, this example is just a scalar, but what I'm doing is more complex because you may have, in fact, a vector of fractions, right? Okay, got it? Everyone got it? So I'm just counting, okay?
So in the summation right after, the I would be
1, 2, 3,
index.
4, 5. Yeah, so in particular, for instance, this would be something like this.
Okay.
To the power of 1, right?
So that'll be the first one. So the in terms of LX, that'll be the 1/2 in this
Yeah.
case.
Then
Okay.
power of 2 and C dot.
Okay. Okay. Okay.
Okay. And then to the last item, right? So the important thing is that this is infinite summation, right? But it still is index, right? That's the key. So so here the important thing is that remember all of these are infinity, but some infinities are larger than others, right? This is the Cauchy intuition, right? So Cauchy the mathematician. So here you have X and Y, and you have two infinite sets, but countable. L of X and L of Y, lower contour sets. Which is bigger? L of X, okay? So now, the indexing, because this is countably infinity, is that the indexing set of X is also larger than the indexing set of Y, okay? Now, each of the additive terms are positive, strictly so, right? 1/2, right? And then for all n, so for all finite integers. So that means, of course, that the summation here has to be larger from X than Y. So there are more terms in the summation X than in the summation for Y. Do you agree? So that means that U of X is greater than or equal to U of Y. Got it?
So sorry. So this is to assume that every item has a non-negative utility, right?
Yeah, so here, remember, the negativity and positivity of utility doesn't matter. The only thing that matters is the ordinal relation. So the only thing that matters is that U of X is greater than or equal to U of Y. Actually, this one even gives you something extra, which is cardinal, and I don't care. But the utility that I'm creating is between 0 and 1, right?
Yeah. So utility cannot be negative. I get it. Thanks.
Yeah. So now we prove also that the other way around, right? So imagine U of X is greater than or equal than U of Y. Okay, so this is the other direction. Got it? So now if I have U of X greater than U of Y, then what does it mean? So it means that U of X minus U of Y is greater than or equal than 0. So if I subtract the first sequence of summation minus the second sequence of summations, then I have two cases, right? The first one is that I have something equal to 0, in which case the indexing numbers have to be exactly equal to 0 because each additive term is strictly positive, right? So the two sets have to be the same, in which case the lower contour set of both are the same. But transitivity means that X is indifferent to Y, right? So which is covered. So X is above Y weakly. Now, the second possibility is that this difference is strictly positive, in which case the indexing set of X is a strict superset of the indexing of Y, which means X is strictly above Y, which together implies that U of X greater than equal than Y implies that X is better than Y. So, and in the 4 minutes I have, I'm gonna end the proof. Because remember that I didn't, so I actually did another example here, right? So I'm gonna erase the previous one that I did for Tyson. To keep the proof clean. And now I want to finish the proof. Remember that I wanted to prove it for all X, so not only for the rational numbers, okay? So, so what was the property I told you that is important here? Is that they are dense inside the Euclidean space. So I take a sequence of fractions or vectors of fractions, and they are gonna converge to any vector of real numbers. Got it? Okay, so what I'm gonna do is use that property to create a utility function defined over the whole Euclidean space. So from the previous theorem, I know that a rational preference defined on the rational space have a utility representation that I created in the previous lemma. In fact, I also know that this thing lives in 0, 1. So is a bounded sequence, is a bounded utility. Now, remember Q is dense in R, and also it turns out that QL, so the vector version, is also dense in RL. So this means that any point in X is either in the rational set or in the, or there is a sequence of rationals, of fractions, that will converge to the real number, okay? That's the definition of being complete or dense. The real numbers are complete space and the rational are dense inside this. So a first try will be to define a utility function, V, this is a new utility, on any item in the reals, right? So any vector. And this will be defined as the limit of the sequence of utilities that I created in the previous step. So V is a new utility defined as a limit, filling in the blanks with the previous utility. So the previous one is defined on the rationals, right? So there are holes in the space. You see, for instance, what is the utility of pi? I don't know, right? So I need to fill in the blanks. So the way I'm gonna do it is, remember that I am gonna use continuity here. Continuity is the important thing that is gonna allow me to fill the gap. So imagine that I have a sequence of items, xn converging to x. And now I have that xn is always strictly better, weakly better than xn minus 1. So this is an increasing sequence. So remember that the utility of such xn is always between 0 and 1 by construction. So I also know that the utilities are increasing because this is a representation of the binary relation. So I know that the fact that u of xn, this xn is preferred to xn minus 1 implies that u of xn is greater than equal than u of xn minus 1. So I have now a monotone unbounded sequence. So if I have a monotone bounded sequence on the reals, then it has to be a convergent sequence, right? So it has to converge to some point. And now, because of the density result, I have that xn converging to x, right? And I have this sequence of xn and yns. Continuity implies that this relation is going to be preserved in the limit. Therefore, u of xn greater than u of yn will be preserved by limits. That means that v of xn is greater than equal than v of vy. So in other words, what I'm going to do is basically fill in the blanks using the limits to create the V utility, which is defined in the whole reals, okay? And that's the proof. Another way to do it will be using a Rubinstein construction, which is taking the supremum over these utilities that are defined on the rationals, basically using all the items in the lower contour set. So I take the lower contour set of any item in the real space, and I take the supremum of the rationals, right? And this is gonna be, of course, if it's a real number, it's gonna be a limit as well. And then the final part is that I also claim this utility I created is continuous, right? And this follows from a mathematical result we're gonna not prove in this class. It's too advanced, it's for second years of decision theories, and it's called the De Vree's gap theorem, okay? So with this, I'm done in this class. So I'm gonna still, let me pause it. Okay, and I'm going to now stop sharing and stop I'm gonna take questions. Okay. So if you're fine, I'm gonna take questions also with the recording device so people can benefit from it. So yeah, so thank you, and you're free to go. I'm gonna upload the problem set later. You're gonna see it on out. Okay. So anyone that has questions now, I'm gonna remain here for the last 15 minutes.
So for the last proof that you're doing, the Q I think was bounded 0 to 1, I believe. Wasn't sorry, I don't know if I remember correctly, but the utility has to be ever increasing. So was it okay to have a bounded sequence?
Well, remember that these things, right? So the 1 is gonna be the limit, right? So you're never gonna reach it, right? So
okay. So it's still ever increasing, but it's just actually not gonna reach. So the set itself is bounded, but you actually the set within elements will actually never reach.
Exactly.
Okay.
Yeah. So you're right. So in fact, this thing is bounded, but you're never gonna reach it, right? So in fact, you have to be the top element. So if there is an element that is at the top, then that one will have utility 1, right? But maybe that element, doesn't exist, right?
Okay. Thank you. Also, the main question. So I tried to access the InVision. Before in the summer you had a test, I think, file, and I tried to access the new one. I think you changed the name, and I don't seem to be able to get in for some reason. So
okay, so let me check quickly. Let me share it. So I'm gonna share it right now in the Slack or in the chat of the Zoom faster, right?
Yeah.
So try to access it now, because I changed the link, right? So we'll start anew.
Okay. Yeah, it's good now. So I'm gonna bookmark it and then.
Okay.
All right. Thank you.
I have a question about GitHub. So if I have a fork and I have like the GitHub app on my computer, how do I get it to update when you make changes to your file?
Okay, so you mean that you created your own fork, right?
Yeah, like I didn't know what I was doing, so I was just pressing everything.
Yeah, no, so in the GitHub client, there is a drop-down menu where you can actually select the master. So just go to the master, and then that's gonna be the version I'm using. So yeah, so, but let me see. So if you can share your screen, I can help you more, but.
Yes, 1 second. Oh, okay, no, I didn't quickly. How do I share my screen?
In the bottom of Zoom, it says
yeah. Desktop one. 1 sec, I need to open my settings to allow. Okay, it says I need to leave Zoom and come back, so I'll join right back.
Okay. Okay, so any more questions? I'm gonna be here on a while until.
Yeah, I just have a quick question. So when we were discussing warp and garp, so with garp you said we lose uniqueness, correct?
So garp per se doesn't loses the uniqueness. The issue in the theorem was that our data may be incomplete, right? But for instance, if you have garp on the tuples and triples, it will be unique, right? The nature of the theorem is just telling you that this garp works for any data, and generically, right, it cannot ensure uniqueness, okay? Because the data may be really poor, like the one I show you. Like for instance, in the data in the example that I gave you, there was a last item E, which was never tested in the data, so to speak, right? So you never saw it in the menus that the experimental subject saw. So E can be anything, can be ranked anywhere, right? So in that sense, it's not unique, but it is actually, so uniqueness is actually a function of the data more than garp, right? But that theorem with garp doesn't ensure uniqueness as opposed to the theorem with warp, because that one has rich data.
Okay, thank you.
Yeah.
Okay, I have a question. When we try to prove that warp that and contains all the up to 3 elements the set, so we can get a rational preference. But I just don't know where the non-empty assumption comes from. I mean, in the choice structure, maybe we can give a compare of it, but we can choose an empty, get the empty.
That's a great question, actually, Fan. So the idea of empty choice correspondences, now that we have experiments, right, has become relevant because people say, of course, people can be undecisive, right? So I give you data, I give you a choice set, and they say, I don't want to choose. I want to choose later, defer the choice, or maybe I want to keep with an out of menu option, what is called a default, right? So I may pick something out of the choices. So now, but you have to remember the chapters we're seeing now are things that Mascodel did, right? So this is pretty much theory was developed in the 70s, 60s, until the 80s. And so at that time, people were thinking more than experimental people, than scientists, they were thinking as mathematicians. So what is the main objective of a mathematician is to ensure that the maximization process has a solution. So in other words, non-emptiness was seen as something desirable. So also emptiness is weird because mathematically is well defined, but what does it mean behaviorally, right? So in order to do something meaningful out of it, you have to give additional detail. So you have to say, if empty, now you are picking actually a default, or you are deferring your choice for next stage. But empty itself is kind of a not completely descriptive event. Now, having said that, you're right that this proof depends on this assumption that is very strong, right? So the fact that we're assuming that non-emptiness is killing all these behaviors such as the Condorcet paradox, right? So, so first imagine the Condorcet paradox that we saw in class with the family. And if they have all tuples and triples, but from the triple, they don't choose anything, right? Obviously, it's not rational, right?
Okay, thank you.
Can I share my screen now?
Sure.
Okay. So, share. So, yeah, this is like the app.
Mm-hmm.
And then this is like the website.
Yep.
But so on the app, like I deleted, like what I've been doing is deleting the stuff and then creating a fork again over and over.
Okay, so let me. Can you go back to the GitHub, and can you go there to the master? Yeah. Okay. Can you fetch the origin? So just in the upper part, the origin.
Maybe I need to create a fork.
Yeah, so what I will do is this. So try to destroy that one. So erase the one that you have in your computer. So just delete it. And then, go there to the current repository. Yeah, and trash it. Yeah.
Yeah. And then
now go to code.
Code?
Yeah, now is delete that repository, Nico.
Yeah, it's gone. Oh, this one.
Yeah, delete that one. No, okay. So now let's go back to the other one. Yeah, go there, put code. The green one. Yeah, and said here you can two things. You can actually, for instance, clone it. So open in GitHub desktop. No, again, go back. Go there. Hello. Yeah.
I need to choose.
So change the one. So create a new one. So you have to, yeah, clone it. Yeah, continue.
This one or?
For my own purposes.
Yeah.
Yeah, and then you show it in Finder. Yeah, so then you have everything, right?
Okay, yes.
Yeah.
But then what happens is when you make changes, like I don't see the changes.
Okay.
I think I know what you're talking about. If you go to like the actual like Apple menu, like on GitHub desktop, and then like there, if you put repository, and then pull, it will automatically update in your Finder.
Okay. Okay.
Thank
Yeah, that was my question because
Thank you.
I basically had to be doing that each time. I don't know how
So
to.
I'm going to update it now with the things we did in class, so you can try it now.
Oh, okay.
So I just push the changes.
Okay. So if I go here,
Just write fetch
repository. Oh, fetch or
or pull. Yeah, that one is fine.
I have nothing. I'll play with it and figure it out.
Just see history. Go to history. Yeah, I think that one has my change of. Okay. Yeah. So maybe I don't know, but
Yeah, I'll play with it. I'll play with it.
okay, thanks. Okay. Anyone else? More questions?
So was the problem that it's not posted yet, right?
No.
Just want to
So
make sure.
I'm
It's
gonna
not,
post it. I'm gonna post it tonight or tomorrow morning.
okay.
Tomorrow
Yeah.
morning. And
I
then,
was checking GitHub and I didn't see it, so I just wanted to make
so
sure.
you're gonna see the alert through the Slack.
Okay. All right. Thank you.
Bye, Tyson.